Okay, so the issue that this is something that's always confusing. Um, we always have an x value that represents where we're doing our calculations. Okay, so um, if we have a beam like this, let's say that in this case it's a cantilevered beam coming out from this wall, so that's a fixed joint with the wall. You'd have a force vector there, a couple there, and let's say that there's a downward force here, you know, 20,000. And let's say that we want to calculate the internal loads here, okay? The x value that we use in these problems always represents the distance from the left end to the point that we're looking at, okay? So this would be x. But then when we do our cut, when we choose what to isolate, our cut looks like this. It goes all the way from the left. So these are there up to this point x, okay? And so no matter what our x value is, everything all the way on the left is there, and so are all the points up until you get to that value of x, okay? We just do that so that we can do this calculation, but what we're really trying to calculate are the values at this x. So so when you find your important points, each cut represents all the important points, or represents, change this to, so each cut represents all x values from one important point to the next, but even if your cut represents all the x values from like 0.5 meters to 1 meters, that doesn't mean that so that range isn't telling us anything about what parts of the beam are in our cut. Our cut always goes all the way from the left up to some range of x values. So, okay, so I think I'm done with that. Let's go to the example problem. That didn't help at all, did it? That didn't help one bit. The reason I did that was because I was hoping it was going to help in some way, but I could feel it as it was happening. Okay, let's go to the example, and just feel free to ask questions, and we'll get this sorted out. So, okay, our example was this. So the problem was the one that we did in a few different ways. So we have an upward force of 1,000, a downward force of 500 on each end, and the length was 1 meter. We identified the important points, one here and one here, because there's always ones at the end points. And then the only other one, there's a point force here. And so we're going to have one cut that represents all the values here, x in the range from 0 to 0.5. And we're going to have one cut that represents all the x values in here, x from 0.5 to 1. Okay. So let's do, this is going to be cut 1. This is cut 2. So let's start with cut 1. This is for all x values between 0 and 0.5. This means the round brackets here mean that we're not including the endpoints of this interval. So we're not including the number 0 and the number 0.5. We're including 0.0001 to 0.4999. Okay. And so what that means is this cut will represent everything from so what if x was equal to just something just bigger than 0, 0.00001? Then we would have a downward force of 500 there. And we'd have an internal load here where that's the tension, that's the shear force, and that's the bending moment. Okay? So this is what it would look like if x was at the small end of that range. What if it was at the big end of the range? Then we'd go still from the same point with this downward 500 Newton force. But now this distance is from here to here is going to be 0.4999. Okay, so in this case, you know, this is equal to 0.00.01 meters. And in this case, that distance is 0.49.999.2. Okay, so these are all of the things that we're dealing with. Okay, and mathematically we can treat them all in one calculation because this is before we reach that second important point. So our representative cut, I'm just going to draw some representative case. Okay, I'll draw it like this. We know that we have the 500 Newton force acting down. And we know we have the internal loads. We know that this point is all the way to the left, and we know that this point is represented by x, where x is somewhere between 0 and 0.5. Okay, so let's write Newton's laws. The second law says, so add up all the forces, 0, negative 500. Then the tension force, that's in the positive x direction, so T0. V is in the negative y direction, so that's 0, negative V. It's an equilibrium, so they're equal to 0. And now you can solve for those two. So T is equal to 0, V is equal to negative 500 newtons. Okay, so what we've just done is figured out that for every value in the range from this little sliver of material to this piece that's almost half a meter long, the tension is 0 and the shear force is negative 500. And now we're going to do the rotational equation. Our about point is going to be the left. I'm always going to do it that way. So what's the moment produced by the 500 Newton force? Nothing, because that line of action goes right through the about point. There's a moment produced by the couple of M. And then what's the moment produced by the shear force? Negative Vx, yep. So it has a moment arm of x, and it's going to cause a clockwise rotation around the about point. So that's negative, so minus Vx is equal to 0. So we solve for m. M is the bending moment. And you get m is equal to Vx, which is negative 500x. So what this tells us is that bending moment is going to, so what if x is equal to almost all the way down to 0? What if m is equal to 0.000 ... then you plug basically 0 in here and you have no bending moment. But what happens as the x value gets bigger? You get more and more negative bending moments. That couple produced, that internal couple has to get bigger and bigger in magnitude to keep it in equilibrium. We'll graph these out at the end. Okay, so that's the first cut. Any questions about the first cut? So now the second cut, what values is this relevant for? X is in the range of 0.5 to 1. And so this represents everything from this free body. So we have negative 500. We also have the positive 1,000 there, and the internal loads. This distance is 0.50001. Okay? So that's the shortest thing that this represents. And the longest thing it represents is almost all the way to 1 meter. You still have the 500 there. You still have the 1,000 there. You still have the internal loads. And now this distance is 0.99 ... 9. Okay. So notice that both of these two things, as different as they are, they have all the same features. So we can represent it with a single free body diagram that just depends on our variable x. And notice that even though x doesn't include 0, our free body still includes that left endpoint. Our free body always includes the left endpoint. Otherwise, we just wouldn't be able to calculate it. So free body diagram generally looks like this. There's a 500 Newton force. There's a 1,000 Newton force up. There are the internal loads. And this distance is some x value between 0.5 and 1. So Newton's second law. I mentioned this before. If you're more comfortable writing out the table to do this calculation, you can do it. Like, say the origin is here or something, and just go through the table, and it'll do all these calculations for you. But for me, since all of these, it's not too hard for me to do in my head because these moment arms are all just horizontal, and so the only thing producing moments are vertical components of things. And so if you're comfortable doing that, do that. Newton's second law says 0, negative 500 plus 0, 1000 plus T0 plus 0, negative V is equal to zeros. And so the tension is equal to 0 still. No, it's the left side still. Yep. I'm always going to do the left side.
And you just cut contiguously in between them.
Yeah. Right. At some x value in between 0.5 and 1.
But if you're doing the left side, how could it be? The 0.5 is what, 1,000?
So there's the 1,000. This is a free body diagram of everything from the left end to an x value somewhere between these.
He's just restricting x where he writes his function later.
Yeah, that's right. Right, right. But our free body is always going to go from the left end all the way to x. X is what changes. Our first cut had x only represented x values between 0 and 0.5, and our second free body, x represents values from 0.5 to 1.
But wouldn't the 500, the downwards force of 500 not be included if there's x between 0.5 and 1?
Yeah, there's another 500 over here that's not included.
That free body diagram is the whole thing. You're just saying that x is going to be in between 0.5 and 1.
So these are the two boundaries of what we're representing. One is just barely longer than 0.5. The 1,000 Newton force is almost all the way at the end. And then the other one is almost 1. If we went 1 billionth of a meter farther, there'd be the other 500 Newton force acting down on our free body, but we're not quite getting that far.
Oh, you're saying that that's an internal downwards force of 500?
Where? This one?
I guess the left 500 doesn't make sense, being that it's 500, 1,000, 500, and you have from 0 to 1, and you're starting from 0.5.
You're not starting from 0.5.
Yeah.
Starting from 0.
Yeah.
It says x with respect to 0.5.
That's the end point.
Yeah.
The end point is
The x value just tells you where the right end is. The free body always starts at the left end.
goes from 0.5.
Okay, yeah, and so V is equal to positive 500. Okay. So positive 500 here. This is a negative V. So move, V over the other side, and you get positive 500. Our other one was negative. And so now the rotational equation. So we have this acts at a distance of 0.5, right? That would produce a counterclockwise rotation around this about point. And so that's positive 500 plus m minus Vx is equal to 0. So m is equal to Vx minus 500 and that is 500x minus 500. All right, so now we have these piecewise functions. Piecewise functions that represent the tension, as a function of x, the shear force is a function of x, and the bending moment is a function of x. T is equal to, you can think of it as like equal to 0 for x between 0 and 0.5. And it's also equal to 0 for x between 0.5 and 1. Yeah, right. Right. And V is equal to...
Hold on 1 second.
Mhm.
The way you have it written is that T is not equal to 0 or even defined as 0.5.
Yeah, you're right. That's always going to be true. We're never going to have known values at the...
Special point.
Right.
Okay.
But we're just going to assume some kind of continuity. But yeah, really, we don't know values there. The shear force is equal to negative 500 newtons for x between 0 and 0.5, and positive 500 newtons for x between 0.5 and 1. And then the bending moment, M, is equal to, what did we have? Negative 500x for x values between 0 and 0.5, and 500x minus 500 for x values between 0.5 and 1. Okay. And the easiest way to represent that is to plot it. So just plot these three functions. You can, what was it, like pre-calc or something where you spend a ton of time, I guess maybe Calc 1, spend a ton of time trying to figure out how to plot functions. These are pretty easy functions, but we'll get more complicated looking ones. So you could spend all that time doing it, or you could plug it into Excel or MATLAB or Mathematica or your calculator or whatever. But these graphs look like this. Tension, internal tension is a function of x. So if this is 0.5 meters and this is 1 meter, the graph looks like this. Then the shear force. Here's 0.5 meters. Here's 1 meter. It starts out at a value of negative 500 and then jumps at 0.5 meters up to positive 500. And then the bending moment, this is a linear function. It starts out at 0 and reaches a minimum value of negative 250 at 0.5 meters. And then it gets the opposite slope and goes back to 0 at 1 meter. Okay, so if you are concerned about this beam breaking due to internal bending moment, you would be most concerned about it breaking right at the midpoint. Yeah, this is the shear force.
Yeah, no, the weak close.
What?
The graph is weak close, four sides. Like this.
Oh, don't bring it down to 0 at the end.
It's 0.
The, we don't know what is happening at the endpoints, and we're just going to leave it off and make the graph continuous. So we're just looking for like a limit there on all of these. So don't draw it back down to 0. Just continue that value out to the end. Okay. So here are a couple things that you can look for kind of a sanity check on this. So here's some things you can use for troubleshooting. So after you're done, you can use these to make sure your answers make sense. The first one is the x derivative of the bending moment is always equal to the shear force at every point. So look at, well, there's one point where there's no derivative, but every point where you can take the derivative, here, take the derivative of m with respect to x, you get negative 500. On this side, take the derivative of m with respect to x and you get positive 500. So that one, our answer makes sense. Second, anytime you have an endpoint with no horizontal point force, the tension equals 0 at that endpoint. Okay, so let's look at our example. The problem we're doing looks like, where did I draw it? Okay, so here's the problem. At this endpoint, is there a horizontal point force? No, there's a vertical one, but no horizontal. Same thing here, right? So we have no horizontal point force happening here or here. When I say point force, is that just mostly, I just say point to mostly kill time there, or what's the alternative to a point force? Yeah, that's right. So you could have a horizontal distributed force, but if you have a horizontal point force, that's the thing that we care about here. So there's none here. That means that our internal tension should be 0 when x is equal to 0, and it should be 0 when x is equal to 1. Okay, so do we have that in our values? Yeah, we have 0 everywhere. Okay, so that second criterion is met. so far, it looks like our answer makes sense. Okay. The third one. What do you think the third one's going to be? Look at this beautiful like symmetry of conditions I'm setting up at endpoints with no vertical point force. Then V will be equal to 0. That's right, at those endpoints. Okay, and again, you know, vertical distributed loads are what we've dealt with so far. We haven't dealt with horizontal ones, but we've dealt with a lot of vertical distributed loads. This is true even if there's a vertical distributed load, as long as there's no vertical point force. And then the last one, what's the last one going to be? It's similar again. Yeah, if there's no point couple at that point, at the end point, then there's no internal bending moment at those points. So at endpoints, with no point couple, I can't even really imagine what a distributed couple would look like, but I'll leave that open. With no point couple, M is equal to 0 at that endpoint. Okay, so are conditions 3 and 4 met in this case? Well, we do have vertical point forces at both endpoints, and we have, you know, non-zero shear forces there. So, you know, that one's fine. And then for the bending moments, there's no point couples at the endpoints, and these both reach 0 moment at the ends. So everything that we can tell from these conditions says we still believe our answer. Okay, if any of these aren't met, then you need to go back and find an error somewhere. Okay. Okay, let's do one now with distributed loads. So let's say that we have a cantilever beam fixed to the wall. Let's say that it's 2 meters long. And let's not put any external loads on it except the weight. And let's say that the mass is 500 kilograms. What are the internal loads as functions of x? So P of x, V of x, and M of x. This is the first time that we have to think carefully about when we're allowed to treat a distributed load as a point force. Like, remember, weight is a distributed load, right? But so far, we've always just treated it as a point force acting at the center of the object, at the object's centroid. If we did that now, right from the start, we'd get the wrong answers. So we have to think about, like, what makes it okay for us to do that? When can we lump it? And the answer is, once you've made your cut, once you've chosen the body to isolate, that's when you can take the distributed load and treat it as a point force. But before you've chosen that body to isolate, you have to consider it a distributed load. The weight is a distributed load. So so the first thing we have to do is represent this weight as a distributed load. How are we going to do that? That's exactly right. And that's a mass. So the weight would be 4,905 newtons. And we know that it's a total of 4,905 newtons for 2 meters. And so the distributed load for the weight is 4,905 newtons divided by 2 meters, and that's 2452 newtons per meter. And it's a uniform distributed load, so we now have a rigid body problem like this. We have a reaction force there from the fixed joint. We have a couple MR from the fixed joint. And the weight gives us a distributed load, the rectangular shape of 2452 newtons per meter. Before we can do our cuts and stuff, we have to figure out what these external loads are. At the fixed joint. To do that, we're going to isolate the whole beam. And once we isolate the whole beam, once we've chosen that we're isolating the whole beam, then we can treat that distributed load as a point force. So we have this 4905 acting down, and the force, the couple, and that's it. So to find these, we could write out the table, but this is, again, kind of a simple case, so I'm just going to do it in my head. But this is just a rigid body problem, a simple rigid body problem. But Newton's second law says Rx, Ry plus 0, negative 4905 is equal to zeros. The rotational equation says Mr, and then what's the moment produced by the 4905? Yeah, the whole thing is 2 meters. This is acting at a moment arm of 1 meter. It's producing, is it a clockwise or counterclockwise rotation? That's clockwise, so it's going to be negative. Solve for Mr, it's equal to positive 4905. And so there's your Mr, and your R is 0, positive 4905. This is newtons, this is Newton meters. Well, you have to do any that don't occur at the right endpoint. If you got to solve those, because those are going to appear in your cut free body diagrams.
Okay, so if we had a tension at the right endpoint, horizontal, would that
You would not have to solve for it because if you think about how it goes once we make those cuts, the right endpoint never comes up. So you could skip that. Okay, so now what we have is an upward force of 4905 newtons, a couple of 4905 Newton meters, and a distributed load of 2452 newtons per meter. Now we have all the external loads and we're ready to make the cuts, you know, find the important points and make the cuts. Where are the important points on this? Do you remember how that relates to distributed loads?
Is that the point where X is a point force?
No, it is only at places where the function defining the distributed load changes. So in one like this, where the distributed load just follows a single function the whole way, you don't have to make any cuts for the distributed load. Okay, there are no important points defined by the distributed load. So the only ones here are the two endpoints, here and here. And so if you only have two important points, how many cuts do you have to make? Just a single one where the right end falls somewhere between this and this. Just a single cut represents the whole body. All right, so our only cut, cut 1, is going to represent x values from 0 to 2. It's going to represent the whole beam. And so our free body diagram is, you know, some length between 0 and 2. We know that there is an upward force of 4905 on the left. We know there are internal loads on the right. We know that the length is x for some x value between 0 and 2. And so what do we know about the weight force? Now we've isolated it, so once you've isolated it, you can treat it as a point force. If anyone comes up with this, I'm going to be so happy. Yeah, that's exactly right. Just like, so every...
Are you happy now?
I'm so happy, yeah. I was hoping it was going to be someone else, though. Yeah, I'm a little disappointed. So yeah, every meter of material leads to a force of 2452 times that, you know, times 1, 2452. This is x meters long, and so the weight force acts right at the middle of this piece with a magnitude of 2452x. And the moment arm, what's the moment arm of this force? Yep, x over 2. Yep, that's exactly right. So this is x over 2. And now let's go through calculating these internal loads. So Newton's second law says 0, 4905 plus 0, negative 2452x plus t0 plus 0, negative v. I'll just lump those two together into one vector, is equal to zeros. So there's no internal tension. The internal shear force is negative 2452x plus 4905. And then the rotational equation, we're always calculating our moments about the left end point, so there's no moment produced by the 4905. There is a moment of 2452x times x over 2, which is, yeah, and is that a clockwise or counterclockwise rotation? Yeah, so so negative, what do you say, 1276? 2226 x squared. You see, actually, let me just break it up first. So we have a negative moment produced by a moment arm of x over 2 and a force of 2452x. Then we have the couple. Then we have minus Vx is equal to 0. And so m is equal to positive 1226x squared plus Vx. Vx is negative 2452x squared plus 4905x. So you get negative 1226x squared plus 4905x. Okay, so we had negative 2452x squared plus 1226x squared. Those add to give you negative 1226x squared. And then we add the 4905 times x here. This is v times x. So you're multiplying all of v times x. Okay, so let's plot it first. So the tension, this is 2 meters. There's no internal tension the whole way. Then the shear force, when x is equal to 0, we have a shear force of positive 4905, and it, that value gets smaller linearly until you get to, when x is equal to 2, a value of 0 for the shear force. So you just have a linear function like that, where this is 4905. And then the bending moment. When x is equal to 0, oh, we forgot something. Yep, that's right. Yep, I forgot that couple. Okay, so go back up to the free body diagram of cut 1. We should have a couple of 4905. And so that gets added when you go to the rotational equation. That should be added here. And so in our final form, we should have a minus 4905 here. Any questions about that? Sorry about that. Okay, so what's the value of the bending moment when x is equal to 0? Negative 4905. And the peak, it must peak a little bigger, right? I think its peak must be at the middle here. It's negative, so it's that's hard to imagine. Oh no, okay, so no, it's just going to go like this. So this is its peak, and it does that. So now let's think about those 4 conditions. So is dm dx equal to v? So go up to these equations. You get negative derivative of this is negative 2452x. Derivative of this is 4905. Derivative of this is 0. So that holds. Where do we expect, what endpoints do we expect the internal tension to be 0? Either of them? Are there horizontal point forces at either endpoint? Nope, so they should both be equal to 0. So at both endpoints, it should be equal to 0, and we have that. What about vertical point forces at the endpoints? We have one on the left, but not on the right. So we expect the shear force to be 0 on the right. Yeah, it would be if you knew the constant of integration, but there's no way to do that without going through these steps. So we have v equals 0 here. So that holds. And then what about the bending moment? Is there a point couple on either end? There's one on the left, but on the right, we should have that the bending moment is equal to 0. And that's what we have. So this answer makes sense. What?
What does that mean on?
On the right side, that's... Any questions about that? Okay, well, let's take a 10-minute break, and I'll start at what were those, 2:08, and we'll do some more examples. Just keep going through examples with this stuff.